Welcome to the integral test for convergence. So the integral test states that if a sequence A sub n satisfies A sub n equals A of n, where A is continuous, decreasing, and A of x is greater than 0, then the sum from n equals 1 to infinity of A sub n converges if and only if the integral from 1 to infinity of A of x dx converges. So the general reasoning here, so if we have a graph with our decreasing function, right? And we have our data values. So at 1 would be A sub 1. The y value at 2 is A sub 2, etc. Right. So if we look at this integral, we can approximate the integral using rectangles. So note that the definite integral from 1 to infinity can be approximated with left-hand rectangles, left-hand Riemann sum. So definite integral from 1 to infinity of A of x dx is approximately the sum from n equals 1 to infinity of the height of the rectangle is A sub n, and then times the width of the rectangle is 1, right? So each rectangle has height A sub n and width of 1. Furthermore, because we have a decreasing function, right? So because our A is decreasing, we actually have the integral from 1 to infinity of A of x dx has to be less than the sum from n equals 1 to infinity of A sub n. So this is the left-hand Riemann sum. And then we can do the right-hand Riemann sum as well. So for the right-hand Riemann sum, once again, we have our curve. we put in our y values. So at 1, the y value is a sub 1. At 2, the y value is a sub 2, etc. So here we're going to do the right-hand Riemann sum. So for our right-hand Riemann sum, the rectangles we're looking at are based off the right-hand side. So this one is going to underestimate. So this one, we have an underestimation. So we're going to underestimate the integral from 1 to infinity of a of x dx. And we have, therefore, this Riemann sum as the sum from n equals 2 to infinity of the area of those rectangles. So from n equals 2 to infinity of a sub n. Again, our first rectangle that we're using has height a sub 2. So this sum is less than the integral from 1 to infinity of a of x dx. So by this rule, essentially what we have is if the integral from 1 to infinity of a of x dx converges, right, then so does the sum from n equals 2 to infinity of a sub n, since the sum from n equals 2 to infinity of a sub n is less than the other integral, or than the integral. And then we saw in the section 8.2 that this means that the sum from n equals 1 to infinity of a sub n also converges. And I see that I need to update my screen. It appears to be frozen at the moment. I apologize, my internet cut out briefly. So I'm not quite sure what you were able to hear last. But essentially what we have is that if the integral from 1 to infinity of a of x dx converges, then the sum from n equals 2 to infinity of a sub n has to also converge, since that's trapped under the integral. And so that means that the sum from n equals 1 to infinity of a sub n also converges. Again, we've just added on one more piece to a finite sum. Similarly, if definite integral from 1 to infinity of a of x dx diverges, then so does the sum from n equals 1 to infinity of a sub n, since by our first comparison, we had that the integral from 1 to infinity of a of x dx is less than the sum. So since the integral from 1 to infinity of a of x dx is less than the sum from n equals 1 to infinity of a sub n. So essentially what we have here is convergence of the integral is the same as convergence of the sequence. So this is a useful trick to have. So let's go ahead and do an example. Our job is to determine whether this series that is the sum of from n equals 1 to infinity of n times e to the negative n converges or diverges. So we're going to take a of x to be x e to the negative x. Then we need to check, is a continuous? On the interval from 1 to infinity. And that's an absolute yes. And the other thing we need to check is a decreasing? So we can just do differentiation if you like. So a prime of x would be e to the negative x minus x e to the negative x, otherwise known as e to the negative x times 1 minus x. This equals 0 at x equals 1. And we're only interested in from 1 to the right. If we plug in a value to the right of 1, we do indeed get a negative number. And so we do have decreasing. So this is a prime versus a. I'm going to just shift this all down a little bit. So we do know that it is decreasing over where we're interested in. So a meets our required conditions. So from here we have the sum from n equals 1 to infinity of n times a to the negative, times e to the negative n converges if and only if the integral from 1 to infinity of x e to the negative x dx converges. So you can evaluate this integral if we like, or you can try to use some other theorem. So the integral from 1 to infinity of x e to the negative x dx would be the limit as b goes to infinity of the integral from 1 to b of x e to the negative x dx. If we do our integration by parts down the side, take x as our u, that will go to 1 and then 0. And then take e to the negative x dx as our dv, that would go to a negative e to the negative x, and then a positive e to the negative x. We add on the first diagonal, subtract the product of the second, and add the integral of the bottom row. We are looking at negative x e to the negative x minus e to the negative x. Oops, I forgot my limit. So this is equal to the limit as b goes to infinity. Negative x e to the negative x minus e to the negative x evaluated from 1 to b, or the limit as b goes to infinity of, we'd have a negative b e to the negative b minus e to the negative b. And then we would subtract from that. We would have a 1 e to the negative 1 minus e to the negative 1. So this simply becomes the limit as b goes to infinity of, we have a negative e to the negative b times b plus 1. This, of course, is the limit as b goes to infinity of negative b plus 1 over e to the negative b. Sorry, over e to the positive b, which is an infinity over infinity case. So we can go ahead and apply L'Hopital's rule. And we are looking at the limit as b goes to infinity of up top derivative of b plus 1 is just 1. We still have our negative out front. Derivative of e to the b is just e to the b. And this, of course, is just 0. I was perplexed by that giving us a 0 as our integral, because it should not be. If we scroll back up, my screen's not currently scrolling. I found my mistake. I should have had a negative 1. Whoa. I apologize. One moment. All right, trying one more time with the internet. I should have had negative 1 e to the negative 1 when I plugged in my 1. So here's my little correction there. It should have been a negative 1 e to the negative 1 minus e to the negative 1. So that gives us, we have e to the negative b times b plus 1, and then we should have had plus e to the negative 1. Sorry, plus 2e to the negative 1. Or plus 2 over e. The limit of the b plus 1 over e to the b component will go to 0. And then we will also have a 2 over e out front. Now, I apologize for about that. I missed a sign and that definitely messed things up. So we have 2 over e plus that limit, and we wind up getting our final answer is therefore 2 over e for the integral. And so we get that the integral from 1 to infinity of x e to the negative x dx converges. And that therefore means that the sum from n equals 1 to infinity of n e to the negative n converges. So once again, the mistake I made was when I plugged in 1 to my antiderivative, I missed the negative in front of the x. So it should have been a negative 1 e to the negative 1 minus e to the negative 1. I had it so they canceled out. So with that correction, we get an integral value that makes sense. It's positive, but it is finite. So the integral converged and therefore our series converged. So this is a trick we can use. And we will use this trick in the next video to prove the convergence theorem for P series.